Okay, so hello everyone. So once again, I'd like to ask you if you stop seeing something, if the video stops, please say something or make some noise, ideally, because otherwise we won't be able to see it before the break. Same with the sound. If you can't hear, then please raise your hand. I don't know, maybe do something about it. So my name is Dmitry Bykov. And the course this time will be about supersymmetric quantum mechanics. So clearly this has, so there are several layers to it. So there is mechanics, right? Mechanics means classical mechanics. Classical mechanics, quantization, and then there are two ways to go starting from classical mechanics. So this is quantization, which gives you quantum mechanics. And supersymmetrization. So supersymmetry. And this can also be combined. So actually will lead to quantum supersymmetric models. So maybe let me say a few words why about maybe the motivation to study these such models. So maybe the main motivation is that there are some kind of toy models for field theories, for symmetric field theories. So these are reductions of toy models. The theories in various dimensions. And indeed, historically, supersymmetry was discovered in the context of field theory. So quantum mechanics came later, and there were several important papers where supersymmetry was found. So in 4D, so 4D, so it's 3+1 dimensional space time. This was in the papers of Wolfgang Lichtmann. And the Wolf of this was Moscow. This was Python. And also Western Zumina. Papers of Western Zumina. 1974. They were all independent from each other. So this was the German. And at the same time, there were also two-dimensional supersymmetric models were found in the work of Gervais and Sakita. Also. These are 1+1 dimensional models. And so all curiously, all of these models were actually different models. So, particularly in the work of Gordon and Liebman, the supersymmetry algebra was written down. The main kind of key player in this science. And the main model that was proposed was some kind of super QED model. Super or relatively massive super QED model. Quantum electrodynamics. So some gauge theory interacting with matter. So in the work of Volker and Akulov, they dealt with some kind of nonlinear realization of supersymmetry, so nonlinear representation. So representation on some kind of homogeneous space, you could say, not a vector space, but some nonlinear manifold. So this is also nonlinear representation. So it's actually a pretty exotic model. So you could say it's quite an exotic model that they found. And later on it was explained how it fits in the usual in the hierarchy of usual models, usual supersymmetric models. And Wesson-Domina, so first they discovered some what is called the Wesson-Domina model. So it's some kind of self-interaction. Self-interaction, interacting with scalar field. So something like 5 to the 4th theory with supersymmetric partners. So some supersymmetric generalization of 5 to the 4th theory. And then in a subsequent paper, we found also the models with gauge fields. So plus similar to the ones by this one. Gauge fields. And so this in Jerez Akita, it was in the context of string sigma model. So it was actually free 1 plus 1 dimensional theory. So free theory. And this is 2-dimensional, so supersymmetry algebra there is a bit different and so on. So this is roughly the history of the subject in the context of field theory. So what about quantum mechanics? So in quantum mechanics, is it operator? So then in quantum mechanics, the corresponding supersymmetric models were first studied by Hermann Nicolai. So quantum mechanics. So or in general, you could just say mechanics, quantum or not. So quantum mechanics from this perspective is the one-dimensional quantization of one-dimensional field theory. So mechanics can be thought of as one-dimensional field theory. So 0 plus 1d. So this was studied by Hermann Nicolai, who was a student of Julius Wess. In 1976. And then these models were considerably popularized and well, put in the realm of geometry, differential geometry, and so on by the famous paper of Witten, 1982. So Witten related these models to differential geometry. Sigma models, studied sigma models. And since then, many more examples of field theories in various dimensions that meet supersymmetry have been found. And moreover, there is a classification of supersymmetry algebras. So there is lots and lots of models in various dimensions, and there is a classification of supersymmetry algebras. Done by Werner Lam. 77. It basically tells you about all supersymmetry algebras in various dimensions. And many examples from that list have been realized as some kind of Lagrangian field theories. So you can construct representations of the symmetry algebras on fields, various field theories. The main upshot of this classification of time is that there are supersymmetric models. Usual supersymmetric field theories. Usual means, say, without gravity. So rigid, what's called rigid supersymmetry in dimensions. So d plus 1 dimension, where d plus 1 is smaller or equal to 10. So these are those theories without gravity. With or without. And if you allow gravity, then you have one more option, which is 11 dimensional gravity. So with gravity, the 12 dimensions. So supergravity. And in higher dimensions, you can still have supersymmetric theories, but they will involve higher spin fields. And so since higher spin means spin greater than 2, so tensor fields of higher ranks. And to have an interacting theories of such fields, you have to include all spins at once. So these are like infinitely more complicated theories. So in higher dimensions, only theories require. So this one, that one, and there's also higher spin. So this follows from Nam's classification.
Only highest spin. So
no. I mean, no. Involving both, yes. But there are like famous local theorems that say that when you have higher spin fields, you have to include all of them at once. So supersymmetry theories rely on supersymmetry algebras. So I will review a bit what are supersymmetry algebras, and I'll give you some examples in some example in dimension 2. This is useful to motivate the supersymmetry algebras in quantum mechanics, because just out of the blue, it's not really clear why studying those ones somehow follows from their higher dimensional counterparts. So on the one hand, you can study supersymmetric quantum mechanical models as dimensional reductions. On the one hand, supersymmetry is kind of secretly present in some usual quantum mechanical models without explicit supersymmetry, where it helps to solve some spectral problems of some potentials, and has been actually studied by Schrödinger and many people before. But it's like some of the exactly soluble potentials are easily explained in the context of supersymmetric quantum mechanics. So that's another supersymmetry in the presence. Various soluble models. Talk about some of these models, that's some of the truth. So supersymmetric quantum mechanics is actually out of all supersymmetric field theories is the least rigid. The least rigid setup. So there are lots and lots of models that are allowed by supersymmetric algebra in one dimension. Whereas, for example, typically you consider some maximal supersymmetric model in some dimension, it's kind of unique or something like that. So there is a whole zoo of models. Zoo of mechanical models. So I will, of course, cover only some preferred subset of those models. So the structure of the course will roughly be as follows. So first we'll discuss the supersymmetry algebra. These properties with representations. And superspace. Then we'll study some popular models or most known models. Things. That you can find in most reviews or books on the subject. So this is just kind of standard content of some course. And then we'll also talk about some more exotic models. So there are lots of exotic models here. Probably Zoom. With time release, etc. And so there are in principle lots of results on supersymmetric quantum mechanics. Most of them are in some papers. So there is not that much literature where it's consistently kind of formulated everything like as a kind of course and so on. So assembled together. So maybe the most useful book that I will be following in some parts of this course by some guy recently. This is literature called differential geometry through supersymmetric glasses. So you can, it's available online in various places. So you can do a search and hopefully find it. He also has a even more recent book called Wittenbergs, which not only covers quantum mechanics, but higher dimensional theories as well, but has some quantum mechanics there. So he's 2024, I think. So maybe there's some overlap, something. But the book on weakness also has some parts of quantum mechanics. Then there is a paper by Howe. This paper called The Geometry of Supersymmetric Quantum Mechanics. That's just one archive. This discusses the differential geometry of various quantum mechanical models. Then there is also the kind of popular course that many people like having a look at, especially as a kind of quick review of various topics, is by Tom. Some Cambridge lectures. Quantum mechanics. This you can just find online. Let's search in Google or search engine you use. And then, so most of these papers, they discuss the differential geometric aspects of supersymmetric quantum mechanics. Most of them are about, most of the stuff here is about differential geometry. Like I say, there's also another interesting topic related to solving explicitly some problems. Like, in the course of quantum mechanics, you solve some problems to diagonalize some Schrodinger operators. So there is also another well-known review about this of the relation to supersymmetric quantum mechanics by Cooper, Murray, and Sopatne. Called Supersymmetric Quantum Mechanics. That's in the article. I think some subset of those authors, they have some book more or less with the same contents. And then there are some papers that I mentioned along the way on various related topics. A lot of the information is in some papers. So first of all, so let's now pass to the discussion of supersymmetry algebras. Like I say, it's one of the main rules is the science. So the supersymmetry algebra. As a super algebra. So first of all, I remind you what is a super algebra. So super algebra is some vector space called G. That's means what is known as the two grading. So it's a vector space with the two grading. That means that there is some linear operator omega maps G to G, and such that omega squared is 1, density operator. And so its eigenvalues are plus minus 1. And G0 is the eigenspace of, so G0 and G1 are eigenspaces of omega with eigenvalues of plus minus 1. So we will A for any A 0, we will A minus A for any A in G. And this vector space is, of course, it's an algebra, and the algebra, so it's endowed with some product. There's the product. G. With certain properties. So first of all, it's respects the grading. It respects the grading. Means that of the commutator. The commutator commutates among individual vectors. And so this has certain symmetry properties. So symmetry properties are as follows. So AV looks like a Lie bracket, or so this is belong to 0, or A belongs to 0, and belongs to G1. Then it's symmetric in both for if A and B belong to G1, they all belong to G1. And because of the grading, this respects the grading. So yeah, maybe it's a different way. Belong to 0. Then this guy belongs to 0 because of respect the grading. So this is also symmetric. A belongs to 0. Belongs to 1. But in this case, this guy belongs to 1. And this guy belongs to 0. This property. They have an interesting chalk color here. I hope you can see it. So apart from these properties, there is one more property, which is the Jacobi identity or generalized Jacobi identity. So these are all so far these are all definitions of this product, the super bracket, super Lie bracket. So it's bizarre. This is this kind of property 1 is the properties 2, it's property 3. So first we call the usual equivalence, right? So the usual equivalence is when you take the double commutator and you make a cyclic permutation. Guys? So you just cyclically permute it, and that's 0. So how do we generalize it? So yeah, so let me introduce some notation. First of all, if so told you that omega acts on every element by multiplying it either by 1 or minus 1. Then let's call homogeneous element. So let's say that omega of A is -1 to the kind of weight of A or gradient of A times A. So this plus minus 1 will now denote by this -1 to the modulus of A. So to generalize to the coordinates, you basically just need to keep track of this. In fact, maybe not all of these A, B, and C's, they have gradient 1. So in particular, for example, if you move A to the right, you pass through B and C, so you have to collect additional factors of the gradient as you move A through B and you move A through C. So, for example, here it means -1 to AB. That's A, C. Right. And here you can either, this guy, you can think of either moving C to the back or moving B to the back from here, but it gives the same result. So this is -1 to the modulus A and C, and this gradient plus modulus B, modulus C. So this is the generalized covariance. That's a quick way to remember how to get it. So if, of course, if all A, B, and C leave in G0, then all of these factors are just 1. So you get back to the usual case. Okay, so then already follow some simple properties already follow from here. So first of all, you see if A and B belong to G0, then the commutator also belongs to G0, and moreover, the commutator satisfies the usual Jacobi identity. So that means that G0 is in the algebra. It's usually the algebra. And then the commutator of G0 with G1 is G1. So that means that G1 is a representation of the algebra. G0 acts on G1. And then there is another third equation which tells you that something about the tensor product of G1 with G1. So this is the third relation. Yeah, so what is the motivation for this definition? Why we have this generalized Jacobi identity and so on? And of course, there is a simple explanation, is that such objects have matrix representations. So these are basically just theories of some matrices. I mean, it's an abstractization of some properties of matrices. So this matrix representations. For example, if A and B belong to B0, or A belongs to B0 and B belongs to B1, then the brackets, the actual brackets that we defined, can be thought of as this commutator AB minus BA, where now, I mean, there's some kind of user notation, but I mean here that you just think of A and B as matrices. That's really defines product is just a commutator of matrices. That's the point. And it will automatically satisfy the Jacobi identity. That's the motivation for having the two coordinates. And on the other hand, A and B belong to G1. Then the generalized commutator is an anti-commutator. So AB plus BA. So this is another commutator. And in this case, if we know that both elements are odd, or is not odd, so they have gradient -1. So we will use the more common notation, square brackets. In this case, we will multiply. Not square bracket, curly brackets. So just not to be confused about it. Okay. So let's discuss some simple examples of superalgebras. And actually, the ones that we will need, we will only need some very elementary examples of superalgebras or superalgebras with superelementary. But nevertheless, let's discuss some examples. So one of the basic examples is the GL 1/1. So GL 1/1 superalgebra. In this case, these are superalgebra composed of 2 by 2 matrices. So G0 is spanned by matrix E0, which is just a unit matrix. And matrix E1, which is this. And G1 is spanned by 1, 0, 1, 0, 0, and F2, which is 0, 0, 1, 0. So what are the commutators in this algebra? And this is a vector space of complex numbers. So you can take arbitrary linear combinations. Yes. So what are the E0 central elements? So it looks with everything. Let's see if it's the unit matrix. And other non-trivial commutators are E1, F1, F1, F2, and this one is F2, and the second commutator F2 is 0. So in general, in dealing with such objects, there is some kind of useful trick, which is as follows. So you see, if you want to take some commutator, super commutator, or some general element. So the small Yes, it's one convenience when dealing with these algebras is that if you want to take a supercommutator of two general elements, for example, sum of I plus sum beta I sum I prime plus sum beta I prime I. We have to remember that some of these are commutators, some of these are anti-commutators, right? So there's a y, for example, alpha j prime, e I with j, plus some cross terms, plus say b I j prime, anti-commutation for that j. So you see, although this is a super Lie bracket here, so it's an abstract bracket. So we have to remember some of these are commutators, some of these are anti-commutators. And this is a bit inconvenient because, well, this linear combination is just some, so if we want to think of it as just some matrix, right? So for example, this is alpha 0 plus 1, 0 plus alpha 1, that means beta 1 beta 2. And that's how we cannot deal with it with a single matrix. We have to always split it into these odd and even parts. So that's a bit inconvenient. So to get rid of this drawback, we can actually think of betas as being Grassmann numbers. So as means involves that. It's a purely technical tool. You don't have to do that, but sometimes it's useful. So think of this Grassmann numbers. So that means, remind you, Grassmann numbers are anti-commuting variables. So that means that anti-commutator. So these are not elements of any superalgebra, they are just formal anti-commuting variables. These are zero, means that each of these squares to 0, and they anti-commute between each other. In this case, such a finite vector space where you use you take linear combinations of the even generators with usual kind of numbers and the odd generators with Grassmann numbers, then it becomes just the usual Lie algebra. So you can use just usual commutators. What I mean is, for example, that beta 1. So now this is usual commutator. Beta beta 2 F2. This is commutator, not anti-commutator. This is just beta 1, beta 2. So let's divide it. So this is beta 1, 1, 2. 2. 1. So if you swap the positions of betas, you get beta 1, beta 2, and second commutator of 1 over 2. So if you view these objects as elements of just usual Lie algebra, you automatically get the super Lie algebra structure that you want. So in other words, the idea is to consider this Boyton matrix as having usual numbers ascending over diagonal, and so these are usual numbers. So we do just usual complex numbers, and these are Grassmann numbers. And in fact, this is not completely artificial procedure. And it's actually necessary if you want to define super Lie groups, Lie supergroups. So the usual relation between algebras and groups is that you can initiate an algebra and get a group element. So, for example, if we want to write G alpha beta, the group element, the exponent of this linear combination. So some then in order for this to have the correct multiplication properties, you should actually assume that betas are Grassmann of variables. Right? So we assume that these are Grassmann variables. These are Grassmann of. And alphas are usual numbers, or it could be just Grassmann even elements of a Grassmann number. Yes. So even then the multiplication will be the usual multiplication. So gamma alpha beta times G alpha beta G alpha beta prime will be G alpha tilde beta tilde, where alpha tilde is a function of alpha prime, the tilde is a function alpha prime, beta prime. So functions like this. Because you use the Baker-Hausdorff formula to combine the exponents, and then there you have the usual commutators. So if you assume that betas are Grassmann variables, then these usual commutators will become anti-commutators for the corresponding the algebra elements, the S. So it was actually this kind of procedure was developed by Berezin and called the Grassmann envelope. This way of taking linear combinations where the parity of the coefficients is the same as the parity of the algebra elements that they pair with, right? So this is called the Grassmann envelope. But it's also just that, so it seems inevitable when you want to go to the supergroup. So this is a supergroup element. Supergroup elements. So you have to do that to construct a supergroup. But say if you work with the superalgebra, you may or may not want to do it, but it's often useful because then you can just commute the matrices as usual matrices and not split them in some even and odd parts. I mean, of course, you split it in your minds by doing this cross, but you don't have to actually split it in the computation. Okay, so let's study some useful subalgebra of GL1/1. So the useful, there's a useful subalgebra. Which is specified by the condition that the supertrace is zero. Supertrace occurs when the matrix ABCD is by definition A minus B is zero. So this tells us that D equals A. So actually only the generator E0 will survive. The generator E1 is not allowed. So S1/1 expand. This expand E0. And mutation relation occurs before, so zero and zero leads to the Rotation relations. It's another useful it's about growth. This algebra. It's real form. So the real form of real powers, which are u1 slash 1 and su1 slash 1. So these are superalgebras over the real numbers. So the basis. So it's 0, 1. So you can check that structure constants are real if you take these combinations, and over real numbers means we're only allowed to take real combinations, different combinations of the guys with real coefficients. And in the supersymmetry course, we'll study the unitary representations of these superalgebras in some Hilbert spaces. We will study some spaces. Unitary algebra or some Hilbert space. So that means that the generators are represented by some permission or superpermission. So the generators are mapped to permission. We will always like to work permission operators. So permission operators with respect to some scalar product in the Hilbert space. Permission operators. So remember the Hilbert space is some there's a vector space with some scalar product. So so these are some elementary examples of superalgebras, and actually we will not need more complicated superalgebras, I think. Or maybe sometimes we will mention some of them, but mostly we'll just need these elementary ones. But before passing to these elementary ones, let's recall. So let's get recalls. That elementary ones. So first of all, say that supersymmetry algebras in various dimensions are a subset of superalgebra. The main superalgebras classified by class. But I mean, supersymmetric algebras are specific examples of those. In particular, they're characterized by the fact that the G0 with these algebras splits as G0 some space-time, so some space-time symmetry, direct sum, G0 internal symmetry. So this is what is called usually flavor symmetry, which is some global symmetry your theory can have. And space-time symmetry is some isometry, the algebra of the isometry group of your space. Isometry or possibly conformal algebra of your space-time, where your theory is defined. Algebra of some space-time. So some, I mean, usually one considers the Minkowski space or anti-de Sitter space, or some similar manifolds. Space-time where your theory is defined. So this is kind of the physical input that allows to single supersymmetry algebras, and this is what was done by now. 1977. He made a much more refined picture of this. But I'll give you an example. So the example will be two-dimensional without any dimensions. Well, this will ultimately explain why I talked about this SU1, 1, 1, 1, 1. So now, for the moment, we forget about those. We just consider the superalgebras in. Okay. There's a video problem. Okay, it's still the same problem as last time. So I should. It's a matter of where I plug this and that. Swap them next time. Please speak up if the video turns off, okay? Because I don't want you to be looking at the black screen. Please Google. Okay, now there's this same problem. Okay, I hope it will not persist. Or maybe shall I make a 2-minute break and switch this? Yeah, hold on, guys. We'll make a 2-minute break and I'll switch the video. Okay, I hope there will be no more problem with the video from now on. But please, if there is a problem, tell me. Some problem with plugging the video input. So as an example, let's take Minkowski space. With magic movement. So the isometry group is also one. This semi-linear product is one. So the generator is the Lie algebra is spanned by the generator J. It belongs in S1. And so the generator is PU. So 0, 1. It belongs to R1. And so, yeah, it's important to say that the Lorentz group S1 from 1 is just R plus. So positive real numbers. That just Yes, I mean, this guy can be written as dx plus dx minus. And our plus scales plus goes to lambda x plus. X minus goes to lambda inverse x minus lambda.
So there is no second component corresponding to negative real.
Maybe there is. I mean, maybe it's just there's a plus. Yeah. Plus. Yeah. I can decide as later if you like, but yes, there are some components maybe. That's just we're just interested in the algebra anyway, so I just want to say that it's one-dimensional and abelian. So. So the algebra looks J plus minus. So minus to be plus or like code in momentum. So and P mu is mu, so P plus to P minus is 0. And so this is a so this is G0. So this is G0. So now you group G0. So in this case, there's no internal symmetry group. There's the space-time symmetry group. And now we want to add G1 to this to have a superalgebra. So G1 will be so we saw before that G1 is a representation of G0. So we take the sum of two one-dimensional representations with charges 1/2 and this 1/2. So W by denoted by W with one-dimensional representation. But there are representations of R plus. That means that, say, some element of Y belongs to W. U, that Y scale is number to the power Q. 1. So in our case here, that's square root of 9. And so we will have two the algebra elements, one living here, one living here, which we call Q plus and Q minus. So Q plus W 1/2. And then to belong to W minus 1/2. And the commutators are as follows. So first of all, so presentation of this local algebra. So J with Q plus minus plus minus 1/2 plus minus. And then we have the so Q commutes to P. So P plus minus P mu Q plus minus 0. And we have another trivial commutators are Q plus with Q plus Q plus. Yes. And Q plus with Q minus is 0. So this is the trivial extension of the Poincare algebra, which is the super Poincare algebra. You see the this has charge 1/2, this 1/2, this has charge 1, so that's why we've chosen charge 1/2. It's compatible. Okay, so this is the superalgebra in 1 + 1 dimensions. Actually, I mean, just for reference, this is what's called 1,1. 1,1 supersymmetry in 1 + 1. 1,1 means that there is one what is called left moving supercharge and one right moving supercharge. So one is as a because a priori we can just set, say, q minus to 0, and that's still allowed. This would be the 1,0 supersymmetry. Here
so you mean G1 could take only one representation?
Yeah, well, this is slightly more exotic from the point of view of field theory, so just we do this more symmetric case. Okay, and now what we want to do is now we want to do dimensional reduction to one dimension. So what will happen after dimensional reduction? So we get rid of the Lorentz generator. And we set and get rid of P1. So it's not P1 to 0, it's the momentum along the space direction, if you like. And we say that P0 is the momentum. And physical P0 and P1 are components of two momentum. Yeah, so P0 is there and P1 is the momentum in 2 dimensions. So we set momentum to 0, we get we just get dimensionally reduced theory. And it's also, in this case, there's no plus and minus in the sense that it's useful to relabel. There's no plus and minus because there's no rank group. So we relabel to plus to 1. Okay. And minus to 2. And then the algebra will simply degenerate to U1 from J equals delta Ij H. So this is the main object. So this is the one-dimensional one dimension. What's called is n equals 2. Again, there are different notations, but usually n equals 2 supersymmetry. 1D. N equals 2 here refers to the fact that there are two supercharges, Q1 and Q2.
So Q1 with Q1 is H and Q2 with Q2 is H.
Yes.
So two supercharges.
Yes. Yes. And they in fact use each other. But actually, this notation, so you often, I mean, for those who are not that familiar with supersymmetry, that is, you often see this notation n equals something supersymmetry. That's dimension dependent. So, for example, here we have n equals 1 supersymmetry in 2 dimensions, and it is dimensionally reduced to n equals 2 supersymmetry in 1 dimension. So this in every dimension you take the minimal spinor representation of your Lorentz group, and if you add the minimal number of such representations in your G1, that's called n equals 1. If you put more representations here, then you increase n. But of course, this representation of Lorentz group, it depends on the dimension. And say, in a reducible representation in higher dimension will decompose into several irreducible and lower dimension, so on. So that's why this notation is dimension dependent. So from now on, I will only speak about one-dimensional things. So here n will be unambiguous. It will refer to this kind of algebra. There's another convenient way to rewrite this algebra. As follows. So pass to complex supercharges. So pass to complex supercharges, which are so here it's assumed, of course, that, for example, in 2 dimensions, all of these generators are represented on some Hilbert space of your 2-dimensional field theory as Hermitian operators. So that's why we call this real, and these real supercharges. It's assumed that these are Hermitian. You're supposed to study unitary representations of these algebra, where Qi and Qj are Hermitian, Y and H are Hermitian operators. That's why we call them real supercharges. And we can also construct complex supercharges just by taking linear combinations. So if you complex by 1/3 of 2 to 1, then Hermitian conjugate, 1/3 of 2 to 1 minus F2. Then the combination relations are divided 0, and Q is to the number. Also, it will find. In particular, this implies that actually, I mean, this is same Q squared is 0. Some which will be useful later. So Q is this complex charge Q is nilpotent. Square is 0. So let's discuss the simplest representation of this super algebra. For example, representation. Is by taking what we call in physics we call a fermion psi. In one dimension, there are not really bosons or fermions, which just mean like anti-commuting and commuting variables. So it's again, that's like a use of language, but it's borrowed from higher dimensional theories. So here, psi squared is 0. Psi squared is 0. Psi value is 1. And the representation is as follows. So we take some vacuum vector, we go vacuum vector, we characterize by the fact that it's split from psi. And then we construct a one particle state, which is another vacuum vector. Then follows that side here, and the y is 0. And so what psi does is there is this state 0, state 0, state 1, and psi is here, psi other is here. Yeah, so psi 1 is 0, which is 0. So it's a two-dimensional representation. Well, representation in the sense that we can now set, let's say how psi is related to q. So we just set q equals psi. We got h equals 1.
So this identification.
Yeah.
So it is, and what's the notation for this algebra? I mean, for the reduced, after reducing to one dimension, if there is a standard letter.
It's n equals to supersymmetry.
No, I mean, because we started like with some G, and for this it is like some letter. No.
You mean for this one? Or
Yeah, for the reduction.
I mean, no, it's before that. After the two-dimensional one.
Okay, yeah, from here. So this is the representation of this algebra.
Of this algebra, which is the same as this algebra. Yeah. Yes, but the point is that why we look at this, that this is actually SU1/1. Yes, if you want to name for this. This is SU1/1. Why? Because basically Q1. So basically Q and Q is F1, and Q dagger is F2, and H is E0. Right? We took some real form, but real form just says that these Q1 and Q2 are kind of Hermitian. So that's why I mentioned the superalgebra SU1/1, because it's actually the supersymmetry algebra in the simplest supersymmetry algebra in one dimension. It can be obtained by dimensional reduction from 2 dimensions. So that's the best name for it. Let's already the 2-dimensional one because we will need this. So of course, there are also you want to generalize this notion of algebra to arbitrary number of generators, right? You can just say that Qi j delta I j h with I j running from 1 to n. So this is n equals n, supersymmetry algebra. Okay. So this is n standard supersymmetry if n is greater than 2. So we will, well, in this course, I will mostly look at n equals 2 and n equals 4 algebras. So let's separately write out the n equals 4 algebra. Here it's useful to pass to the doublet of complex supercharges. Q alpha 1. We're now alpha is 1 and 2. Now we go complex guys. And the algebra is Q alpha with beta is 0. So it's Q alpha dagger is Q alpha beta dagger. It's 0. But it's Q alpha and Q beta. Double alpha beta H. So this is n equals 4 supersymmetry algebra. And curiously, this also can be obtained by dimensional reduction from 4 dimensions. So this can be obtained from maybe obtained. n plus 1, theory in 3 plus 1. I mean, in 4D, there's no left to right moving. I mean, and as long as you take a single wild spinor supercharge. The supercharge you take a single wild spinor, so it's a single spinor of SL2C, two-dimensional representation of SL2C. It's SL1 3 as a multiple of SL2C. And you take a two-dimensional spinor as your supercharge. And it's a complex two-dimensional spinor. That's why it decomposes into 4 real supercharges in 1 dimension. So if you just forget the action of SL2C, it's a 4-dimensional real vector space. That's why you get n equals 4. So okay, so let's discuss some main properties of this supersymmetry. Supersymmetry algebra. Before we finish today, so there's some couple of main properties. So this supersymmetry algebra leads to some properties of the spectrum of your Hamiltonian. So just to stress that this is how supersymmetric quantum mechanics differs from non-supersymmetric quantum mechanics. That the Hamiltonian is part of some algebra, the central element of some algebra, and not just like hanging in the air in usual quantum mechanics. And so this is some consequences for the spectrum of this Hamiltonian. So first of all, H is positive vector, right? Because this is for n the number of supersymmetries from 1 to m, from 1 to infinity, because H is twice I squared, right? So negative psi plus the norm like Q1 I squared. So equal to 0. And there's a slight improvement of this. That's a slight important improvement. If H has a 0 vectors, as an eigenvalue 0, then it's annihilated by all QRs. Okay, and the third main property is that for n greater or equal to 2, the spectrum H at least doubly degenerate. Sorry, so spectrum H with spectrum, positive spectrum. So that means positive energy. At least generator. Graph is here, so H equals E. Just sit on a eigenspace, and then we go to E. We get that over with here. Q squared. Rho squared is 0. And then, so Q squared is 0 means that Q can be represented as a and a certain number of Jordan blocks of size 2. Jordan block gives a double degeneracy, and if you have more than one Jordan block, you can have higher degeneracy. And I think next time we'll study the general N case, and we'll pass to explicit examples of supersymmetric systems, where we'll see how all this works. So I'll wrap up for now, especially because I'm out of battery. Somehow it's not charging. Are there any questions or comments? Yeah, I don't see any questions. So then if you have any questions, you can write on the WeChat group or send by email or something like that. So see you on Friday.